A PEM electrolyzer looks simple on paper. Water goes in, electricity goes in, hydrogen comes out. That's the clean diagram everyone sees. But inside that cell at the microscopic and material level, there is an entire engineered system under stress. Electrochemistry, heat, pressure, fluid flow, and rare materials all interacting at once. And the reality is this. The difference between a lab demonstration and a bankable hydrogen project is not whether this reaction works, it's whether this system survives. So this is not just a step-by-step explainer, this is an inside-the-machine investigation. We're going to follow every layer, every reaction, and every constraint, from water entering the system to hydrogen leaving under pressure, and then push one level deeper into what actually determines performance, efficiency, and long-term failure. Because in PEM electrolysis, the chemistry is the easy part. The system is where everything breaks. We start with the structure. A PEM electrolyzer cell is a compressed stack of layers, what engineers call a sandwich architecture. At the center is the membrane electrode assembly, or MEA. This is where the electrochemical reactions happen. The MEA consists of a polymer membrane, with catalyst layers bonded to each side and porous transport layers pressed against those catalysts. Surrounding this core are bipolar plates, in which distribute water and gases, collect current, and connect each cell in a stack electrically. Everything else in the system, pumps, rectifiers, separators, heat exchangers, is there to support this one compressed structure. And this is where the first non-obvious insight appears. PEM performance is not defined by a single component. It is defined by how well every layer interacts under real operating conditions: temperature, pressure, hydration, and current density all at once. Water enters the system on the anode side, and not just any water. This must be highly purified, deionized water. Even trace contaminants, ions, metals, organics, can poison the membrane or catalysts. This is not a suggestion, it's a hard operational constraint. So already, before any hydrogen is produced, you have a dependency: water quality infrastructure. The water first encounters the anode bipolar plate. This is typically made from titanium, and that decision alone tells you how aggressive the environment is. The anode side operates under highly oxidizing conditions. Stainless steel, which would be cheaper, would corrode rapidly. Titanium survives, but at a cost. And this cost scales directly with electrolyzer size. The bipolar plate contains flow channels, precisely designed pathways that distribute water across the entire surface. If distribution is uneven, current density becomes uneven. That creates localized heating, membrane stress, and accelerated degradation. This is why flow field design is not a detail, it is a core engineering discipline. Because if flow is wrong, everything downstream suffers. From the flow field, water moves into the porous transport layer. This is a conductive, porous structure, often made from sintered titanium. It has to do two things at once: allow water to reach the catalyst layer while also conducting electrical current efficiently. These are competing requirements. Increase porosity and you improve flow but reduce electrical contact. Decrease porosity and you improve conductivity, but restrict water movement. Every PEM system is balancing this trade-off. Then the water reaches the anode catalyst layer. This is where the reaction begins. Water molecules are split into oxygen, protons, and electrons. The reaction itself is straightforward. The difficulty is not the reaction, it's forcing it to happen efficiently, repeatedly, and without destroying the materials involved. The catalyst here is iridium oxide, and this is where the system hits one of its hardest physical limits. Iridium is one of the rarest elements on Earth. Global production is measured in single-digit tons per year. Now consider what PEM scaling actually means. Gigawatts, potentially terawatts of installed capacity. The math does not comfortably close. So already at the catalyst layer, the system is under constraint. Not from physics, but from geology and supply chains. This is what Renee Energy calls system stress. The reaction works, but can it scale? As the reaction proceeds, electrons are released and travel through the external circuit. This is your measurable current. Meanwhile, oxygen forms and exits the system, mixed with water, and must be separated before the water is recirculated. But the most critical movement is not the electrons, it's the protons. These must cross the membrane. The membrane is the core of the PEM system. It is typically made from Nafion, a polymer that, when hydrated, allows protons to pass while blocking gases and electrons. This is what enables separation: hydrogen on one side, oxygen on the other. Without this, the system fails both in performance and safety. Inside the membrane, protons move through hydrated channels via a mechanism where they effectively hop between water molecules. This means hydration is not optional, it is essential. If the membrane dries out, conductivity drops sharply, resistance increases, and efficiency collapses. Now layer on another constraint: thickness. A thinner membrane improves efficiency because it reduces resistance. But it also increases the risk of gas crossover, hydrogen leaking to the oxygen side. That's not just an efficiency loss, that's a safety issue. A thicker membrane improves safety but reduces performance. So again, the system is balancing competing forces. And over time, the membrane degrades. Reactive species attack the polymer structure. It thins, it weakens. Eventually, it fails. This is not hypothetical, it is one of the primary lifetime limits of PEM systems. Now the protons reach the cathode side. Here they combine with electrons to form hydrogen gas. The catalyst here is platinum, supported on carbon. Platinum is expensive but less constrained than iridium, and the environment is less aggressive, allowing for more material flexibility. Hydrogen forms at the catalyst surface and moves outward through the porous transport layer and into the flow channels. And this is where PEM reveals one of its most important advantages: pressure. Unlike alkaline systems, PEM electrolyzers can operate with differential pressure. The hydrogen side can be maintained at much higher pressure than the oxygen side. This means hydrogen is effectively compressed as it is produced. And this has major system implications. Compression is one of the most energy-intensive steps in hydrogen infrastructure. If you can reduce or eliminate mechanical compression, you reduce both capital cost and energy consumption. But again, this advantage comes with stress. The membrane must maintain integrity across this pressure differential. If it fails, you don't just lose performance, you lose containment. The hydrogen exits the system with water vapor and trace impurities. It passes through separation, drying, and conditioning stages before reaching the required purity levels. And purity matters. For many applications, fuel cells, ammonia synthesis, refining, impurities are not tolerated. Now zoom out from the cell to the stack. A single cell operates at around 1.8 to 2 volts. That's not enough to produce hydrogen at industrial scale. So cells are stacked, dozens, hundreds of them, connected in series. Voltage increases with each cell. Current determines production rate. But stacking introduces new constraints. Compression must be uniform across every cell. If pressure varies, performance varies. Thermal management becomes critical. Hotspots accelerate degradation. Fluid distribution must be consistent across the entire stack. One poorly fed cell can limit the entire system. And then beyond the stack is the balance of plant, the system that makes everything actually work. Power electronics convert AC to DC. Water systems maintain purity and circulation. Cooling systems remove heat. Control systems monitor every variable: pressure, temperature, voltage, flow. This is where the biggest misconception in hydrogen exists. People think the electrolyzer is the product. It's not. The system is the product. And this is where economics enters. Because every inefficiency we've discussed, membrane resistance, catalyst loading, flow distribution, compression, translates directly into cost. Specifically, the levelized cost of hydrogen. If efficiency drops, electricity consumption rises. If utilization drops, capital costs are spread over fewer operating hours. If degradation accelerates, replacement costs increase. This is why utilization is one of the most important variables in hydrogen economics. A PEM system operating at high utilization can approach competitive cost levels. The same system operating intermittently, tied to variable renewable energy, can see costs increase dramatically. So now step back and look at the full system. Water enters under strict purity requirements. It flows through titanium plates and porous layers. It reaches an iridium catalyst constrained by global supply. It splits into protons, electrons, and oxygen. Protons cross a hydrated membrane that must balance efficiency, safety, and durability. Hydrogen forms at a platinum catalyst, exits under pressure, and is conditioned for use. All of this happens inside a stack of compressed cells supported by a complex balance of plant, operating under dynamic conditions. And every layer, every interface, every decision is a trade-off. This is why the real question is not, does PEM electrolysis work? It clearly does. The real question is, can this system operate reliably at scale under economic constraints over long periods of time? Because that is where projects succeed or fail. And this is where understanding the system, not just the chemistry, becomes critical. If you are developing, financing, or evaluating a hydrogen project, this is the level of detail that determines outcomes. Not the reaction itself, but everything around it. If you want to go one step further into how these physics and engineering realities translate into actual project economics, this is exactly what H2 Hub is built for. You can model PEM systems with real parameters, efficiency curves, capital costs, utilization scenarios, and see how small technical changes cascade into financial outcomes. Because in hydrogen, nothing exists in isolation. Chemistry becomes engineering, engineering becomes cost, and cost determines whether the system survives. And that's the core insight. A PEM electrolyzer is not just a device that splits water. It is a tightly constrained system operating at the intersection of physics, materials, and economics. The performance of the entire system comes down to two things: the quality of each layer and how well those layers hold together under stress. In the next step, when you compare this to alkaline electrolysis, you'll start to see something even more important. Not which technology is better, but which system survives under different conditions.